Selector. And it is my pleasure to introduce our first speaker today, and that is Chris Wirth. So Chris is a junior at Harvard, and for the past year has been working with the TESS team on searching for planets around young field stars. And the title of his talk today is Mapping the Orbital Obliquities of Young Planets with TESS. So Chris, if you could share your screen, and the floor is yours.
Awesome, thank you. All right. Hello, everyone. Welcome. Thanks for the introduction. I'm a junior at Harvard College. My name is Chris Wirth, and I'm studying astrophysics and physics. And I'm really excited to talk about the incredible field of young exoplanet research with TESS, specifically through the lens of obliquities. Yeah, it's awesome. So we believe planet formation is believed to only last about 10 or so mega years. And as that's the time scale for gas depletion around solar type stars. But that hardly means that the structure of a planetary system is static after that point, as dynamical evolution can last until the stellar host is 100 mega years to even a giga-year or so old. And so it's believed that a system's orbital obliquities can trace the dynamical history of the system. And so the orbital obliquity, also known as a spin-orbit angle, is the angle between the spin axis of the star and the orbital axis of the planet. And so this cartoon that I made shows some possible formation pathways of something like a multi-planet system of Neptune-sized planets. And so we see Neptunes or super Earths around 30 to 50% of sun-like stars. And so that makes them a really important demographic for us to be able to understand. So in the middle pathway, you can see our prevailing model for the formation of these systems, as the planets will form in situ in denser regions of the disk, and then migrate through the disk to their observed location as warm Neptunes. And so this will lead to what we commonly see as a system of warm Neptunes, and they'll be well aligned. And so what that means is we have a small obliquity angle, a small angle between the stellar spin axis and the planetary orbital axis. And if we had a large angle, we'd call that misaligned. And that's something we can get in the bottom row, for example, where there would be a torque on the already formed system by some sort of external companion, or in the top row, where as the system is forming, we would have some external companion providing a torque on the system. And so since both of these mechanisms would lead to misaligned planetary systems, or something we have like Pluto, where we would have an orbit that's out of whack with the star's spin axis. But since these mechanisms would require some sort of companion, we expect we would see most Neptunes to be well aligned. So what do we see if we look at all the planets that we have age and obliquity measurements? So let's just look before NASA's TESS satellite launched, all the planets that were discovered before that. And so this is what the graph looks like. We would expect well-aligned or prograde planets to show up down near the bottom of this graph, polar planets in the middle, and retrograde planets at the top. And so we can see that there are a lot of misaligned planets. And if we restrict this to planets smaller than 6 Earth radii, we choose this number, even though I'm saying Neptune size because young planets tend to be inflated, we get something that looks like this. And so before TESS came along, we can see we have more misaligned small planets than well-aligned ones. But since these are some of the most abundant types of planets in the galaxy, we would expect, if our theories are right, to be seeing a lot of well-aligned planets if they form so commonly. So the question becomes, when and how did all of these systems over here get tilted? And so to answer this question, it's really difficult right now before TESS because we have this huge gap on the left side of this diagram. Right, so that means we have no information on any planets younger than 200 mega years, which is, longer than the time scale for dynamical evolution usually. And so without any of these data points, it's really hard to answer this question of when and how these systems get tilted, because we just don't know what happened in the early types and in the early stages of a planet's life before we're able to measure it here. And so an interesting question is, why did we have this gap before TESS? So younger stars tend to be more active. They have star spots. That leads to a lot of rotational variation in the light curves, and it makes it much harder to find planets, to the point where ground-based surveys can't really pick them out. And even though K2 found a lot of young stars, we just got unlucky, and they were too dim for us to really be able to follow up. But now with TESS, and it's that's NASA's Transiting Exoplanet Survey Satellite, incredible mission launched in 2018. It's able to take pictures of the whole sky, sectors at a time, and it has, being space-based and state-of-the-art NASA technology, we've got some good photometric power, and we're able to really pick these systems out. So that really is going to be able to, as we get more systems to try to fill in this gap here, going to be able to help us answer these questions. For example, the discovery of TOI 942 as a planet host was announced last year by 2 different papers in the bottom right. And so while many young stars are identified as such by their membership in something like a young cluster or an association or a moving group, TOI 942 is just a field star that was picked out purely through TESS. And so since young stars tend to be more active, they often exhibit the rotational variability that we can see in these 2 sectors of TESS data. And so these observations can be analyzed to pick out this characteristic shape caused by the rotation of star spots in and out of our view. And so I believe this could be a really powerful tool to find more and more potential young stars in the future. So around this star, 2 transiting planets were identified, one in pink and one in blue, with the inner planet, TOI 942b, in a 4-day orbit, and the outer planet, TOI 942c, in a 10-day orbit. And both of these planets are, roughly Neptune-sized. So just because we have rotational variability in a system doesn't necessarily mean that it's young. So to confirm that this is a young star, spectroscopic measurements were obtained by the discovery papers. They found clear lithium signature, calcium HK emission, X-ray emission, and all of these combined for an age estimate of somewhere around 60 million years. So since most obliquity measurements had previously been of Jupiter-sized planets, and due to the scarcity of bright young planet hosts, even though the system is at 12th V magnitude, it presented a good opportunity for follow-up. So to follow up and to measure this obliquity, the Mclaughlin effect was used. And this effect is when a transiting planet will first, for example, the star is rotating, the side that's rotating towards us is blue shifted, the side that's rotating away from us is red shifted. And then the transiting planet will go in front of that, first blocking out the blue light, making the star look overall redder, increasing the radial velocity that we measure. And then goes across, blocks the red light, makes the star look overall bluer, and decreases the radial velocity, as if it's pointing away from us, as it goes across. And it'll produce this characteristic radial velocity signature in this bottom panel here. Of course, it'll do it in reverse if the planet is retrograde, but that's not what we found for this specific planet. So to obtain these radial velocity measurements, we used the Planet Finder spectrograph on the Magellan telescope in Chile. We observed 2 partial transits of TOI 942b, that's the inner planet, at the end of 2020. And so immediately in the second panel here, you might notice it looks different from what the animation shows, and the best fit model would confirm that. So the reason for this overall trend that we need to fit is because spots on the stellar surface will move across on a much longer time scale, and they'll dim the star much more than the planet if they're dark spots and the star is rotating slower than we see the planet go across the surface. And that'll cause a large scale variation that we can easily fit with a polynomial. But one thing we wanted to be sure of was what happens if our planet were to cross in front of a spot. And so we cooked up this exaggerated model with these huge spots. And we saw that if a planet were to cross the spot here, it would cause this huge dip in the radial velocities. And so, of course, this is wildly exaggerated to show the effect, but we wanted to make sure that something like this wouldn't affect our measurement. You can see it again. As it goes across this spot, we have a dip in this radial velocity. And so to test this, to make sure that this wouldn't mess anything up, we modeled the spot distribution of our star using the PFS spectral line profiles. And we found that this configuration here on the left was going to be the best fit model with these spots in this configuration. And so if we remodel now, using the baseline brightness of the star with these spots taken into account, remodel the Mclaughlin effect, just tweaking the parameters so that we make sure this planet goes in front of the spot so we can check what it would do. We found that if a spot crossing event were to occur, it would cause this 0.5 meter per second bump in the radial velocities that we can see in this bottom panel. And so if we go back here to our measurements, we can see that a 0.5 meter per second bump is much smaller than the error bars on the measurements themselves. And so that means that it wouldn't be detectable by any means by our relatively uncertain measurements of the radial velocity. And so this is already accounted for in our measurements. And so we don't need to worry about that. So with this check, we could be confident uncertainty is accounted for. We can just detrend away the overall star spot effects with something like polynomial. And this is the final detrended phase folded radial velocity plot with a beautiful pro-grade Mclaughlin effect. And so this effect is parameterized by the obliquity projected onto our line of sight. So previous obliquity measurements of planets have sometimes had trouble differentiating the projected obliquity and then going from that into a three-dimensional obliquity not projected onto our line of sight. But since we have TESS, we have an awesome light curve, and we're able to know the rotation period of the star and derive, just with some geometry, derive the full three-dimensional obliquity of TOI 942b. We're able to see that it's very much prograde. So now if we go back, let's remember what the distribution of obliquity versus age looked like before the TESS mission for less than 6 planets, less than 6 Earth radii. Okay, what about now, about 3 years after the launch of TESS? So we have, using TESS's young planet finding abilities, we now have 3 planets younger than 100 megayears, all with obliquity measurements, all small and prograde. And all of these were discovered with TESS, which is awesome. Here they are back in context with all of the larger planets. So drawing any conclusions from this now would definitely be too early, as we only have a few data points. But as of this moment in time, we don't currently see any young misaligned planets, which is definitely interesting. So where do we go from here? How can we continue, to get to a spot where conclusions can be made? So what I've been working on recently is to try to increase this sample by finding more young planets that are able to be characterized with this obliquity measurement. And so using TESS, we picked out a planetary signal around the star TOI 4399. And this is a pretty bright star at V magnitude of 8, which is really exciting. Great prospects for follow-up. So we can see here from its TESS light curve that we have clear rotational variability, which makes it hard to pick out the transits. I could not see a transit here by eye by any means. But if we fit a Gaussian process model to the standard to the stellar variability, divide it out, we can see that we can get a detrended light curve that looks like this, and we can clearly see 3 transits. Well, easier to see because I highlighted them, but we could, we're able to see them. You can see the dip here in the non-binned light curve. The darker, larger points are binned to 30 minutes. And so we can see that with something like a 30-minute observation cadence, this transit here is only, the bottom of the transit is only 4 data points if we had a 30-minute cadence. And so we got lucky with this star in in the fact that it was already submitted to have an increased cadence because it had some other, it was just some overall study of sun-like stars. And so, without an increased cadence, it would be much harder to pick this out, which is one of the reasons that TESS is so good anyway, because, even at TESS's worst cadence, we're able to get something. Whereas, previously it's much more difficult to do something like this. And so since this is such a variable light curve, as I mentioned before, we wouldn't really be able to pick this out from the ground by any means. So here are 3 gorgeous TESS transits. Okay, just like the other system, it doesn't necessarily have to be young because it has this rotational variability. So we need to have other ways we can see the youth of the system. So one way is we obtain some radial velocities of the system, and we know the proper motions from Gaia, and so with those 3 vectors, we're able to see its true three-dimensional motion of the star. And if we trace that back, a few 100 megayears or so, we can see that it lines up with a bunch of other stars. And so this is what I was talking about with something like a young moving group. And so the true three-dimensional velocity of this star is in line with other stars in the AB Doradus moving group, which was first announced in 2004, has been expanded ever since. And the exact age is disputed, but it's somewhere around 100 megayears. And so that tells us that this star is somewhere around 100 megayears. Definitely young, definitely interesting. And the lithium, we measured lithium of the star as well, and the rotation period versus color. They all line up with the other members, providing further evidence this is likely around 100 megayears old. So now that we know that it's a young star and it's a young mini Neptune, of course, we want to go back now and do things like measuring the obliquity. However, due to the noise of this light curve, because it's a young star, there's a lot of uncertainty on parameters like the transit center timing, the period, that kind of thing. And so when those errors propagate, if we want to go back in something like 5 years to measure something, to continue to characterize the system as our technology gets better and better, we might have no idea when the transit occurs. And that, since time on these things is so expensive, we can't, that's not something we can really afford to let happen. So we went back with CAOPS, which is a European photometric satellite, to get another transit. And it looks like this. And so, if you haven't seen CAOPS transits before, you may be like, why do we have all these gaps in the data, and why are all these bumps? Why does it kind of look bumpy to the sides? And so this is in a polar orbit around the Earth. And so so these gaps are from, Earth blocking our star, and then the horns to the side are from the satellite looking through kind of the twilight of Earth as Earth is about to block the view. And so, but this is a really powerful satellite. We're able to catch the transit, further refining our parameters, enabling follow-up observations years and years down the line. So that's awesome. And now we can see that the planet is about 3 Earth radii and a 7.71 day period, lies here against the California Kepler survey of planets. And so highlighted on this plot in blue are planets with ages less than 200 megayears. And we can see we have a dozen or so small young planets that we have detected so far. The samples only is growing by the minute. Hopefully soon we'll be able to measure the obliquity of TOI at 4399b, which will further allow us to fill in the plot that I was talking about before. But for right now, this is one of the brightest, youngest, smallest planets we have. It's a lot of qualifications, but it's a really exciting target. So yeah, that's all I have. I'd love to take any questions.
Thanks very much, Chris. That was an excellent talk. It's great to see these young planet systems being discovered, and with obliquities too. It's really, really interesting. So do we have any questions for Chris? If so, please raise your hand in the with the raise hand function. Okay, there are no immediate questions, so I'm going to go ahead and ask one. Chris, I was wondering, have you tried using your in-transit spectra to look for atmospheric contributions from your planets, such as from H alpha?
Yeah, so this we haven't really done that because these, for 942b, the spectra aren't that high resolution, even though the radial velocities have pretty big error bars, and so that's something we definitely could do. Like I'm sure we'd be able to get something out of it, but the error bars on a measurement like that would be not really interesting. They would kind of cover all the possible options. It could be anything at that point. Yeah.
Yeah.
But with a better spectrograph, we absolutely could.
Thanks. Erwin, you have a question? You're currently muted at the moment, Erwin.
Now I should be unmuted.
Yes.
Okay. Since the main topic of this talk was on obliquities, I couldn't help but notice that the one graph you showed of obliquities had quite a few what I'd call retrograde obliquities, more than 90 degrees. I was wondering if this distribution in its present state was able to tell you anything at all about planet formation that may explain this obliquity, or that would be explained by this obliquity distribution.
Yeah, sure. Here, I can share it again. So that was from start. All right, so we're talking about the graph here. So for planets that are larger than 6 Earth radii, there are lots of well-characterized methods in which a planet could be thrown around dynamically and end up in a retrograde orbit. For small planets, that's kind of one of the things we're trying to answer, and so we don't have a lot of ideas about exactly what could cause this, other than the presence of an external companion, and so that's something we've seen take place in systems like I don't think I have any of them labeled here, but in systems that are on this side of the graph. I don't remember exactly which ones we've characterized, but that's definitely something we've seen take place, dynamically modeled. Okay, there's an external companion in it, and it could have tilted the system such that we have the planets lying in these wacky orbits. But other than that case, that's kind of what we're trying to figure out, what could be going on.
Thank you.
Any more questions for Chris?
Oops.
When you still have your hand up, is that it? Okay? Any other questions? I have an additional question, Chris. So earlier on, you were showing like a model assuming a spotty star and how that would change your Mclaughlin measurements. I was wondering if you could explain again how you constrain the star spot properties that you were assuming for your model.
So this one, like this here, yeah. So basically, it's called we use the spectral line profiles. And so basically we're able to see that the, even though they aren't quite good enough to get something like H alpha, in the lines themselves of the star for the various various elements, absorption lines, we're able to see, as the broadening has to do with this side of the star rotating towards us, this side of the star rotating away, and so we can see like little bumps and stuff in the lines that correspond to the spots as they're rotating in. So kind of similar to how the Rossiter-Mclaughlin effect is caused itself. These spots will block the redder part of the broadening of the lines, and so we'll get a line that's kind of bumpy in the certain way corresponding to these spots. And so that with higher resolution spectra, that can actually be used instead of the Rossiter-Mclaughlin effect. You can actually see the shadow of the planet moving across if you're able to do that. But since in our case we find that the spots are quite quite darker compared to the planet, we're not really able to differentiate the signals.
Thanks. Okay, so if there are no more questions, then thanks again, Chris. And we'll move on to our second speaker. So Ryan, if you could go ahead, please.
Yes, so I'm happy to welcome our second speaker, Charles Law. So Charles is a fourth year PhD student and an NSF graduate research fellow here at Harvard University, where he's working with Karen Oberg and Qizu Zhang on the chemistry of star and planet formation. So we're going to hear a lot about this from Charles in a moment, but I think it's worth noting that Charles is actually a part of the MAPS project, which is now that famous project that became famous, I think, just last week for its absolute bombardment of the archive on Wednesday, where I counted 20 papers from MAPS, and 2 of which are going to be or have been led by Charles. Charles also has an interest in science communication, particularly in increasing access to STEM careers for all participants. This includes Charles's participation in the Harvard Summit for Young Leaders in China, where he actually developed and taught a 2-week-long astronomy course in Shanghai, China. So now I'm happy to hand it over to Charles to hear more about what he's going to talk about today, which is chemical mapping of.
Is he going to talk in Chinese?
What's that?
Is he going to talk in Chinese?
I certainly hope not, but that would be great for the recording, I think. So Charles, please take it away.
All right. Thank you, Ryan. Thanks for the great introduction. Hello, everybody. My name is Charles Law, and I'm going to be talking to you today about chemical substructures at high resolutions in protoplanetary disks. And this will be all results from the Molecules with ALMA on Planet Forming Scales, or MAPS Large Program. Okay, so just a quick word about the MAPS program in general. This was an ALMA Cycle 6 large program led by Karen Oberg. And in total, it was 130 hours of observing time with ALMA. So substantial commitment by ALMA to look at these targets. And none of the work I'd be able to show today was without the hard work of all of the team members here. So we have 39 astronomers across many institutions, 8 different countries. And it's really their tireless efforts over these last 2 years that I'm able to show you anything today. And as Ryan noted, there are 20 papers now on the archive. So this is a timely talk. They've come up on archive on Wednesday. So they've all been accepted and will be coming out in a special issue for the AppJ supplement series sometime next month. So look out for that as well. We also have our website. Please check out ALMA MAPS, where you can see a summary of everything, download all the data, and I'll talk a little bit about that at the end. So today I'm just going to be talking only a subset of the results. Can, as you imagine, not get through all 20 papers. I'm going to be talking about MAPS 3 and 4, which are the papers that I led, and these explore the radial and vertical disk structure respectively. Okay, So the aim of MAPS was to reveal the chemistry of planet formation. So in order to do this, we targeted a comprehensive set of molecular lines. So this is over 50 different molecular lines. And these let us basically select particular lines that gave us vital information about the disks. So gas density tracers, such as CO isotopologues, molecules that gave us access to elemental ratios, so where the carbon, nitrogen, oxygen, sulfur are, deuterated molecules to get us access to the D to H ratios, photochemically sensitive molecules, as well as molecular ions. So really to get the most comprehensive picture as possible. These were all observed at very high spatial resolution, so down to 10 AU scales. And this was important because it provided access to the chemistry going on in the inner planet forming zones of these disks. And moreover, it allowed us to probe both the radial and the vertical structure of the gas in a fine level of detail. And in doing so, that also allowed us to assess the relationship between the dust and the chemical substructures that are found within these disks. So it's those two latter points that I'll be talking about today. Okay, so the 5 disks that we observed with MAPS are shown here. So they are all relatively nearby, no further than 160 parsecs. Some of them are around T-Tauri stars and some are around Herbig-Ae stars. So the top row here is showing the 12CO 2-to-1 emission. So these are integrated intensity maps showing where the molecular line emission is. Something you'll notice is that they're very bright and they're very extended. So they were in fact chosen for this reason. They have bright and extended molecular line emission, making them good targets to perform a chemistry survey on. What you'll also notice is the bottom row here shows the continuum emission in the millimeter. So this is tracing the millimeter-sized dust grains that are residing in the disk midplanes. And a diverse set of substructures are present here, from spiral arms and IM loop to tightly nested concentric rings in AS209. And again, we wanted to survey disks with a wide range of continuum substructures in order to assess how this impacted the chemistry. And perhaps most importantly, all of these disks had evidence of ongoing planet formation, really making them ideal targets to study the chemistry of planet formation. Okay, so moving on to disk radial structures. So why do we care about disk radial structures? We know that the spatial distribution of gas and dust sets the composition of the nascent planets that are forming in them. And thanks to some really great observational work in the last few years, we've seen that dust substructure at the 1 AU to 10 AU scale, so at very small scales, is ubiquitous. We see lots of rings and gaps and spiral arms shown in these nice 2 surveys here to the right. But we also expect the gas distributions to have similar substructure. We know that there should be gradients in the carbon, nitrogen, oxygen ratios in both large and small organics. But so far, line observations have been limited to coarser resolutions that would not be sensitive to these substructures, or they've been focused on a single line, such as CO, or towards a single disk, which has in general precluded conclusions about the chemistry going on in wider sets of these disks. And to emphasize this point, I'm just going to focus on one disk here, the disk around HD 163296, one of our MAPS targets. And here I'm going to compare the continuum observations in the upper left-hand corner with those of some common molecular tracers, so C18O, N2H+, and formaldehyde. And by looking at this, you can see the continuum observations are very well resolved. The beam in the lower left corner is very small. We see a very beautiful image of rings and gaps that you can see pretty much down to the central star. But that's not the case when you look at the molecular line observations. The beams are considerably bigger. The signal to noise is not as great. And we really just aren't able to perform any sort of one-to-one comparison between the dust and the gas. And so we really don't know if there are substructures under basically being hidden by this larger beam. And if there are, we don't know how they relate to the dust features in these disks. So that's exactly what MAPS aimed to solve, to provide us this sort of comparison with the dust and in general survey the chemical substructures that may or may not be present in these disks. So let's jump to some results. So the short answer is yes, there are plentiful chemical substructures. So here to the right is actually only a small sample of the data that we have. These are the emission from 6 different molecules here, just selected to provide sort of a representative sample. Each row is a molecular transition, and then each column is a particular disk. And just glancing at this quickly, what you immediately see is a striking morphological variation, both among different disks and different molecular lines. We see that substructures in the form of rings, gaps, and emission plateaus are observed at virtually all radii where we detect line emission in these disks. And in total, This amounts to over 200 different substructural features across all 5 MAPS disks. Some features have widths that are barely resolved, less than 10 AU, and then some are pretty much plateaus, 100, 200 AU in size. So to illustrate this diversity, we can take a cut along the horizontal axis here. So if we consider just one molecular line transition and look at it across our map sample of these 5 disks, what do we see? So let's look at the HCN 3:2 transition. And when we do this, we see a clear variation among these disks. So the top row again is the integrated intensity, so the spatial distribution of the emission. And the bottom row here is a radial profile showing the intensity as a function of radius, all on the same intensity scale. So not only is the variation very evident in the morphology, it's also very clear in the intensities as well. Something like IM loop has considerably weaker HCN emission compared to a disk like MWC 480 or GM Reggae. So again, just in all ways you can have diversity in these lines among these disks, you do have it. And one other way to look at this diversity, to illustrate this diversity, I guess, is to look at a single disk now. So back to our favorite disk around HD 16296, and to take a cut along the vertical axis here. And now we'll consider all the different molecules that we've observed and then I analyzed in MAPS 3. So instead of 6, let's look at a sample of 18 different spectral lines. So that's what's shown here to the right. So here are 18 different lines that were sufficiently bright and extended to perform an analysis of their substructures. And again, immediately clear that depending on which lines you look at, you see a totally different disk. In CO, they're typically very broad, large, and smooth. Lines such as C2H or HCN have 3 or 4 separate rings. The molecular ion, HCO+, or formaldehyde, they're both very plateau-like in their emission. The more complex or larger molecules like C3H2 or HC3N have a single very compact ring near the central star. So again, just depending on what you look at, you see a totally different molecular face of this disk. But one thing I want to emphasize is now we can actually put the continuum, so the dust observations, on an equal footing with the gas observation. So if you look at the beams here, they're comparable between the line observations and the continuum observations. So what this allows us to do is actually go ahead and homogenize the sample, uniformly analyze all of the substructures. And so that's what I've done here, labeled the radial locations of each ring and gap that we see. So in HD 1639296, that amounts to more than 70 substructures across these 18 lines. But perhaps more importantly, this actually allows us to directly compare with the radial locations of the substructures that we know to exist in the dust. So it's exactly what we do. So the plot here is showing on the x-axis the radial location, and on the y-axis is showing the particular molecular line. And each point here is showing a chemical substructure. So the squares here are rings and the circles are gaps. And the color scale in the background is the dust emission. So bright regions correspond to dust rings and dark lanes correspond to dust gaps. And so we did perhaps the most naive analysis we could, and simply just plotted everything on top of each other and began to search for radial coincidences. Did we see pretty much a random distribution of our rings and gaps, or were things aligning in radial location? And in fact, we found things to align pretty well. So in this case here, you can see that the many rings are in the line emission are aligning with a ring in the dust, and similar case for the gaps. So we have lots of gaps in the line emission aligning with a gap in the dust. Now, this is not always the case. Sometimes we have other associations. So here you can see many chemical rings now aligning with a dust gap, the one at around 49 AU. So we see that things are closely, the gas and the dust are closely related, and we're having radial coincidences that are common, but there's sort of no one size fits all relationship between the dust and the gas. And so this is only one disk. You might ask, did we do this for all of the MAPS disks? And we did. So here's somewhat of an overwhelming slide. I don't have time to show all of the data, but we did this for every single line that we could for all 5 disks and compared them with the dust. And so rather than trying to squint and interpret this plot, I'm just going to sort of jump to the conclusion. And that is that in general, within 150 AU in these disks, that the dust and the gas are well associated. We see links being very common between the chemical substructures and the dust substructures. And that's what's shown here in this plot to the right. we had 4 different ways things can align, because you can have a gap or a ring in the gas, and you can have a gap in the ring in the dust. And so we just analyzed all possible correspondences, all pairs of correspondences that we could have. And if you'll notice, many of the bars here are over 50% of overlapping substructures. Some are as much as 80 or 90%. So that means the vast majority of the chemical substructures in these disks are aligned with something in the dust. Now, again, not in a consistent way. So we don't always see rings aligning with rings or gaps aligning with gaps. We see that this varies both among different disks and even at different radii within the same disk, like HD163296. But overall, this does suggest some sort of physical or chemical link between the midplane where the dust is and the more elevated molecular layers where the line is emitting from. That, again, no one size fits all though. So it's going to be a bit more complex to infer in each case where or why these links exist and what these links are. But it is sort of important. And now we actually have the data to begin unraveling that question. That really on this, you need to understand the chemistry on the small scale if you really want to understand the planet formation that's going to be happening in these disks. Okay, so what about the innermost region? So I talked about the chemistry of planet formation. So within the innermost 50 AU in these disks, which we now have access to because of the high resolution of these observations, we can also ask what is the behavior of the gas like? And it turns out it's equally diverse. So we see very diverse radial morphologies, even in the innermost regions of these disks. So here's the 5 different panels for 5 different disks. We just picked some representative lines, CO in red, HCN, which is a nitrogen bearing molecule, in orange, a hydrocarbon of C2H in purple, and formaldehyde, which is a small to medium organic molecule, in blue. And sometimes they sort of follow each other. GM you can see that they pretty much all follow the same shape, peaking at around 20 AU or so. But in some cases, like MWC480, they're strikingly different, with some molecules rising very sharply and then others having a very large cavity towards the innermost region. So in some cases, these cavities can be explained by dust optical depth, since you have a lot of dust in the center of these disks, but it really can't explain the full diversity we see. There really has to be abundance, excitation, temperature, chemistry variations all going on in these innermost regions between the different disks. And this is consistent with what we see at all radii. Basically, every disk looks different than the other ones, depending on which line you look at. And I guess the takeaway from this is that the planets that are going to be assembling in these disks are likely to assemble in very distinct chemical environments. Now, that would be true across different disks, but also true at different radii within the same disks. And to just advertise one of the other MAPS results. So even if you look at the absolute highest resolutions, this is some work by Arthur Bozeman in MAPS 15, where he used some kinematic information to get down to an effective angular resolution of only 3 AU using the CO isotope log lines. Even at this very small scale, within 10 AU, you're still seeing substructure. You're still seeing rings and gaps, even at the smallest scale. So that means there's really still more to go. It basically, as you keep going down and down, closer to the central star, you still see these substructures, and they don't look similar. These 3 disks look quite different from each other in their innermost regions. Okay, so in the last few minutes, I just want to mention the one other sort of direction we can probe with these nice data, and that's the vertical direction. So all of the MAPS data that we have are image cubes. So that means they are position, velocity, and we have this information in the form of channel maps, which allows us to look at the line emission intensity per velocity channel or per frequency channel. So I'm going to play this video here for HD163296. This is the CO emission. And you can see a very characteristic shape appear, almost like a butterfly pattern as we sweep through the velocity structure. And okay, I'll play it one more time. And this is because the gas is orbiting in a Keplerian rotation around the central star. And so it's tracing this very distinctive pattern, and this is letting us actually, it provides us a ton of extra information, but in terms of what I'm interested in, it gives us access to the vertical emission structure in these disks. And how we can do this is we can pick an appropriate channel. So here we're picking the channel at 7.1 kilometers per second. And here we can actually see both sides of the disk. We can see the front side of the disk and map it out. We can also see the back side of the disk separated. This is because the MAPS disks are at a moderate inclination. And if you look at the right channel, you can infer the vertical distribution of your gas emission, just like this. And to just drive home the point about how much data we have, here is appropriately selected channels for all of our CO isotopologues, 12CO, 13CO, and C18O, for all of our MAPS disks. And if you look here, you can in each case see both the front and the back side of the disk. Sometimes it's easier, sometimes it's a little harder, but in all cases, we can use this to actually map out the vertical structure in detail. And so again, going back to our favorite disk, just to show it as an illustrated example, this works something like this, where the top row here shows the 12CO, the middle shows the 13CO, and the bottom C18O. And we can use this vertical distribution and map it out in terms of get a height as a function of radius. And we see that the 12CO is the most elevated, coming from the highest layer. As we move to 13CO, this is a bit deeper down, closer to the midplane. And then C18O is almost at the disk midplane itself. And you can actually see this directly in the channel maps. As the surface is more separated for 12CO, then it comes closer together for 13CO, and even closer yet for C18O. And this can be understood in terms of the abundance of these isotopologues. The surfaces we're looking at are the tau equals 1 surface. And so as you move from the more abundant isotopologues like 12CO to 13CO to C18O, the tau equals 1 surface gets closer and closer down to the disk midplane. And we can use this fact to basically map out the two-dimensional structure of this disk. And so this lets us do lots of things, but in terms of chemical substructures, we can actually zoom in now and ask the question, do we see variations? Are these surfaces very smooth? And it turns out we do see vertical dips in the emission heights here. So you can notice several here. There's one at 46 AU, there's one at 81 AU, and another at 145 AU. And these are generally consistent among the different lines that we're looking at here. And what I've done is overplotted the locations, the radial locations of the dust features. So the gray dashed lines are the dust gaps, and the solid orange lines are the dust rings. And what it turns out is that we often see the vertical dips at the same location as millimeter dust gaps. And so what this would suggest is that this is due to a decrease in H2 gas surface density and might be due to planetary perturbers in these disks causing this. I don't have time to go into the full explanation for that. Ask me a question if you're curious after this. But the idea is that this might present a new technique to be able to infer the existence of embedded planets that are forming in these disks, where we find correspondences between the vertical dips in the emission surfaces and dust gaps. And this isn't the only disk to show this. I only have this plot here, but this is fairly common that we see these correspondences between the dust gaps and vertical substructures in the MAPS disks. And just want to advertise one extra thing for our MAPS results. This isn't the only way we can find planets using this. We can use these emission surfaces to actually map out the deviations from Keplerian velocity, which is something that Rich Teague has done in his MAPS paper, MAPS 18. And in this way, you're also able to infer the existence of planets just from the gas kinematics itself. So he's able to identify a possible planet at 245 AU and the disk around MWC 480. So we can really get at planets in these disks in several different ways by having this really high spatial resolution data. Okay, so I just want to summarize what we've learned. So we see that we have ubiquitous chemical substructures pretty much at all radii, and with a diversity of widths and depths. We see that planets are likely to assemble in distinct chemical environments across these different disks and even within the same disk. And the emission surfaces that we can now map out in the two-dimensional direction might provide us a new technique to identify embedded planets in these disks. And just very quickly, want to advertise that our website is now live. So we provide all of the data for MAPS is now public. So you can download the measurement sets, you can download all of the line image cubes, all the moment maps and radial profiles, including all of our reduction imaging and analysis scripts. So everything you need to reproduce our results or to work on this yourself. We have this very nice data selector where you can select the disk, the image, the data product, the particular molecular line, the angular resolution, and the product that you want. So this is a tremendous amount of data. So be careful if you select all of it. I think it's 10 terabytes. So just grab what you want. But this is extreme credit to Ryan Loomis for putting this together over the last few months. And 20 papers in the MAPS collaboration is quite a lot. So I advise you to go look at the publications tab where we try to provide a more sort of Reader's Digest version, a quick summary paragraph and a summary figure. So if you're interested in that, then you can click and it will bring you to the archive link and eventually the journal articles links. And to just note the data download here, if you click it, it will actually pre-populate your data download to give you all of the data products that went into that one paper. So if you want a particular result from a particular paper, that's exactly where you can go and just sort of don't have to find it yourself. Just click the preset data download here. Okay, so with that, I'll leave up the summary slide. Thanks for listening, everyone, and happy to take any questions.
Thank you, Charles. On behalf of everyone who's there, thanks for that very thorough explanation of what seems to be an incredibly rich data set. Well, clearly 10 terabytes, so a really fantastic program. Does anyone have any questions for Charles? I see David Phillips.
Hi, great talk. Do you have to worry about optical depths and opacities greater than 1 distorting how we would interpret these nice intensity maps that you're showing us?
Yes, you do. So sort of the aim of MAPS 3 was to sort of provide a empirical classification of all the substructures that we see just in the line intensity. To infer something about gas abundance, you're going to have to do some thermochemical modeling, which is done in the subsequent MAPS papers, because exactly there are other issues like dust opacity, especially in the inner regions of these disks. And it depends. Some are more optically thick than others, but just optical depth alone doesn't explain everything that we see. There's too much diversity for that, but it is certainly a consideration that is relevant. You can't just look at these line intensity maps and think that they map directly onto abundance maps, because that would not be true.
Okay. Thanks.
And so actually, I had a question sort of related to that point, whereas if you look at some of the 2D maps and you see these intensity features that are not azimuthally symmetric, presumably that is an optical depth effect, or are you actually somehow correcting for the geometry of the system?
So that's an excellent question. So in general, in terms of non-azimuthally symmetric features, we don't see any at high significance. So sort of to first order, the vast majority of the lines look symmetric in the azimuthal direction, with the exception of 12CO and GM Reggae, where we see actual infall and spiral arms. But almost everything else is pretty symmetric. And so we don't see the evidence, even in the case of like HD 160-296, where there is some non-azimuthal symmetric dust features, it doesn't really map onto the line emission in any way that we can definitively identify it. But the second part of your question about mapping the geometry, with the emission surfaces, we're actually able to constrain the two-dimensional geometry and use that for the radial deprojection. So when we show radial intensity maps or the radial profiles in the paper, if it was possible to actually constrain the emitting surface, we use that in the deprojection, because that gets you more accurate radial locations. Now, in some cases, it was really only possible for the CO isotopologues. For the weaker lines, we just had to assume that it was coming flat from the midplane, which is perhaps not true, especially for molecules like we know are photochemically sensitive, like CN, that might be much higher up. But we sort of did the best that we could until we get higher resolution, or I guess higher sensitivity data to map out those emission surfaces.
Yeah, so the one that I actually made a note of was 163-296, the HCN map. It looked to be very azimuthally asymmetric, but you're saying that that's just low sensitivity, like that's probably not a real.
So that is the one other molecule where we got a good emission surface. It's about a ZOR 0.1. So what you're seeing there is the emission surface in the moment map. It's a little distorted because it's not coming from the midplane, but that was one of the few lines where we had really, really good signal to noise where we could see that. Now, if you imagine if you degrade the signal to noise, you're not going to be able to see that structure. But yeah, that's a great eye. That is another one where we're able to see it directly.
Okay, thanks. Erwin.
I thought this talk was remarkable. You have an incredible collection of data. It's mind-boggling, really. I had a question about the relative amounts of the various isotopologues and the various chemical elements themselves, whether you tried to trace them back to their star of origin to see whether it made any sense with the model of the star's evolution and so forth, that they should give such ratios, such relative compositions?
Oh, that's a really interesting question. No, we haven't tried that yet. But that is something to think about, to do sort of more comprehensive modeling, starting way back to see if it makes sense to what we get. So that is definitely something to try. Certainly we've only sort of scratched the surface of the data, wanted to get it out to the community. So there's many things that we should do as follow-up. So thank you, that would be very interesting.
You're welcome. It was just a remarkable collection of stuff, really remarkable.
Thank you.
Are there any more questions for Charles? If not, I have one sort of overview question. Okay, so just sort of taking a step back here. I mean, presumably all the chemical species that you're looking at are dictated by what is accessible in the ALMA bandpass. But I'm just wondering, from maybe just from a theoretical point of view, do we have a sense of how those different chemical species actually influence the planet formation process?
What do you mean by influence? Like,
well, so you were pointing out how, you know, if there are planets that are actively forming in these disks, many of them will be forming in chemically distinct environments. And I'm just wondering if people have a sense, people in the field have a sense of what that sort of unique chemistry, how that will affect the final, structure of a planet.
oh, okay, I see. Yeah, that makes sense. I don't immediately know the answer to that question. That is a great question. I don't know how far sort of models have taken it from if you sort of give like the natal environment chemically, what do you predict for the actual planet? I don't know if that's been done. So I can get back to you on that. It's also, I think, not exactly clear what, like we can observe sort of the chemistry in a certain, radial region. It's not clear how much of that is actually accessible to the planet forming, because the planets are going to form in the midplane, right? So if you don't have a good idea of the vertical distribution of sort of what can be actually in contact with your planet and what can't be, and if there's ways to sort of transport things from upper layers down into the planet, which it seems to be the case, you can have flows of gas onto the planet, but I don't think that's sort of been worked out as well, sort of what is in the planet forming zone and what is somewhat elevated and accessible to the nascent planets.
Okay, thank you very much. Well, with that, I think we're at the hour. So let's thank our speakers, Charles and Chris again.